Hello, class. I want to cover the section 3.9 related rates. I'm sorry I'm late doing this, but I had a bad reaction from my COVID booster. So anyways, I'm back in action now. And so this is 3.9 related rates. And in a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. The procedure is to find an equation that relates the two quantities and then use the chain rule to differentiate both sides with respect to time. So this is a real simple example. The radius of a sphere is increasing at a rate of 4 millimeters per second. How fast is the volume increasing when the diameter is 80 millimeters? So we need to find an equation that relates the radius of the sphere to the volume. And so this is the formula that's for the volume of a sphere, and it is in terms of the radius. I would give you this formula if this was on a test. You don't need to go and memorize every formula that's out there. Let me see, I am recording, aren't I? Let me just check. I think I am. Let me just stop for a second. Okay, so I just wanted to make sure I was recording everything. So I take the derivative of each side with respect to time. And so because R and V are two different variables and time is a different variable than those. So the idea is that as this sphere, it's like a balloon, it's being blown up, the volume of the balloon is changing as the radius changes. They're both changing, and they both change as a function of time. So the longer it's blown up, the bigger it gets until it pops or something like that. So we're taking the derivative of each side of the equation with respect to time. So on this side, it's just going to be dv dt. On this side, and since that's just v, I mean, it's like if it were x and we took the derivative of x, it would just be 1. Or if it was y and we took the derivative of y, it would be y prime. So this is like a v prime. You could even call that v prime if you wanted to. Then on the other side, we are going to use a chain rule. So we bring down the 3 and multiply it times the 4/3 pi. And then we subtract one of the from the exponent, but because we have to use a chain rule, that'll be times dr dt. Because remember, r is a function of time. So it's just like if this were y squared or 4/3 pi r cubed, y cubed, you would do this and you would have y squared times y prime. It's the same thought. But with both of these, we end up having to multiply times the derivative of whatever the quantity is with respect to time. Now, this is why it's called a related rates, because once we take the derivative, these derivatives are rates of change. Remember, a derivative is a rate of change. So now we have a relationship by a quantity or a number of different rates of change. So this was given. If you look up here, the rate of change of the radius is it's increasing at a rate of 4 millimeters per second. And we want to know how fast the volume is increasing at the moment in time when the diameter is 80 millimeters at that moment in time. So it's an instantaneous rate of change. So I know that this is 4. That was given. And this is what we're looking for, the dv dt. So I can just substitute in the 4 for dr dt, and then I can substitute in a value for r. If it's the moment in time when the diameter is 80, then the radius is 40. So I substitute the value in for dr dt, and I substitute in the value for r, and then I should be able to get my answer. So I substituted in this 3's just cancel. And then I substituted in 40 for R and 4 for the dr dt. And then it gives me 25,600 times pi millimeters cubed per second. Okay, so the idea is you find a formula or an equation, and it may come about from the geometry of the problem. Sometimes, or a lot of times, what we use is Pythagorean theorem, because when we draw it out, we have a right triangle. And then you find that formula, and then you take the derivative of each side with respect to time. Then you have your related rates, and you should have been given some rates, and you substitute those in. You will have probably another quantity or two that you will have to derive, but you should have enough information to derive that. Like in the problem, it was said at the instant in time, or it didn't say instant in time, but it's when it says when the diameter is 80 millimeters, it means the instant in time when the diameter is 80 millimeters. Well, if the diameter is 80 millimeters, the radius is half that, it's 40 millimeters. So then we can substitute everything in and we get our answer. That's how fast the volume is changing at that moment in time. Okay, so when you're doing a related rates problem, the problem solving strategy, it's useful to recall some of the problem solving principles from page 83, that's in the textbook, and adapt them to related rates in light of our experiences in example 1 through 3. Now, I'm not, I don't know I forgot what example that was. Let's just look at this list of strategies. So you want to read the problem carefully, and that may take reading it several times. Sometimes I'll read it a couple times, get an idea, maybe draw a picture if that helps. And then I'll draw the picture and start working on it. And then I always go back and read it again just to make sure I understand. Draw a diagram if possible. And it doesn't always make sense to draw a diagram, but sometimes it's necessary. Introduce notation, so assign symbols to all quantities that are functions of time. Like in the case, the example a minute ago, it was the volume and the radius. And then express the given information and the required rate in terms of derivatives. Write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution. Use a chain rule to differentiate both sides of the equation with respect to t, and then substitute the given information into the resulting equation and solve for the unknown rate. Okay, so let's look at this next problem. And it says, at noon, ship A is 150 kilometers west of ship B. So you might not be given the diagram, and you're going to have to draw this out. So ship A is 150 kilometers west of B. So say this is where ship A starts out, and this is where ship B starts out. And when we start, there's 150 kilometers between them. Now, ship A is sailing east, so it's going this way. And ship B is sailing north, so it's going this way. And then we have the rates for ship A and ship B. How fast is the distance between them changing? The ship's changing at 4 p.m. So what you want to think about is, for one thing, what are we looking for? What are they asking for? Well, they're asking how fast Z is changing, the rate of change of Z, because this Z is the distance between them. And I should have said that. X is the distance that ship A travels by 4 p.m. And so then that makes this side, if it had been 150 and ship A is traveling this way and it's gone X miles or kilometers, then this side is 150 minus X. It's not 150 anymore because A is moved. And everything's moving. That's the thing. Everything's changing. Y is the distance that ship B travels by 4 p.m. And Z is the distance between the ships at 4 p.m. So we want to know how fast this distance, or what is the rate of change of this distance between the ships at 4 p.m. Okay, so when we look at what we've got, we have a right triangle. And a lot of times what we use with the right triangle is the Pythagorean theorem. So you know, the Pythagorean theorem says that this leg squared plus this leg squared equals this leg, or the hypotenuse squared. Because the hypotenuse, the side across from the right angle, is always the c. So it's like a squared plus b squared equals c squared. So in this case, this side is 150 minus x, this side is y, and this side is z. So I put it into the Pythagorean theorem, and this is the equation that relates the quantities, x, y, and z. Now I'm going to use implicit differentiation is really what I'm using to find the derivative of the left-hand side and the derivative of the right-hand side. So I'm going to take it, and with respect to time. So I'm going to take the derivative with respect to time of the left-hand side and the derivative with respect to time of the right-hand side. So I bring down the 2, subtract 1 from the exponent, and multiply times dz dt. Or like you could call it z prime. It's like y prime when you're doing implicit differentiation. And then I go to this term, I bring down the 2, subtract 1 from the exponent. I multiply using the chain rule times the derivative of the inside. And because there's a minus x right there, the derivative would be, of 150 would be 0, but the derivative of minus x would be minus 1. And then I have to go times dx dt. And then I take the derivative of y squared with respect to time. So it's 2y times dy dt. Now we're looking for dz dt. That's what we're looking for. We were given dx dt and we were given dy dt because that's the rate of change of ship A. And this is the rate of change of ship B. And the problem gave us that, is it told us how fast ship A is sailing east and how fast ship B is sailing north. So now what I do need is X and Y, because if you look at after we've, you know, really what we've got to do now is we've got to fill everything in, and we should have enough information to fill everything in except this dz dt. So we're going to need to have X and Y and Z. But we can, because we know how fast ship A is moving. It's 35 kilometers per hour. So in 4 hours, we know how far it has moved. It's, ship A has moved or traveled 150 kilometers. And the same thing for ship B. This is ship B's rate. And so in 4 hours, it's 100 kilometers. So we can go ahead and put that in. X is 140 and Y is 100. Then we can use the Pythagorean theorem just to find Z. So Z is going to be the square root of, this is 10 when I go 150 minus 140. So 10 squared plus 100 squared, because you know Z squared equals, or C squared equals A squared plus B squared. So to solve for C, I would take the square root. So that gives me the square root of 10,100. Now you can leave it in this format to get the best answer at the end. The more you round, the more error you're going to have, or the earlier you round, the more error you're going to have. So let's wait to round. So I go to fill everything in. And so I fill the Z in, substitute in for Z, and I substitute in for X. So I know X is 140, and I substitute in for Y, which is 100, and I've got my rates. And then I can solve for dz dt. I just need to divide by 2z. That's where this came from. So then I can substitute all in my calculator and get approximately how fast the distance between them is changing. And it says 21.39 kilometers per hour. And this is the rate that the distance between the ships is changing. And that's just where I put it on my calculator. Okay. So that's a typical related rates problem. So you see how you had to draw the picture. A lot of them are like this, where you have to draw a right triangle and use the Pythagorean theorem. But you want to write down your quantities that are involved in this problem. And it's a good idea to figure out which one am I looking for? I'm looking for the dz dt. And I was given the dx dt and the dy dt. I didn't write them up at the top, but I wrote them down here. And then I have enough information to find x, y, and z. And so then when I substitute everything in, I can solve for the dz dt. Okay. Now let's look at the next problem. You know, this, if I was teaching face-to-face, I would have my students try this. It's a real simple problem. So each side of a square is increasing at a rate of 7 centimeters per second. At what rate is the area of the square increasing when the area of the square is 64 centimeters square? So we've got a square and each side would be the same. So we're going to call it x equal the side of the square. And we're looking for the rate of change of the area. And we know the rate of change of x. So we're given dx dt is 7. And we're looking for dA dt. So write out the formula for the area of the square. It's x squared. And then differentiate each side with respect to time. And so dA dt equals, or this side the derivative of this respect to the time equals the derivative of this with respect to time. And this is what we're looking for. And then I bring down the 2, subtract 1 from the exponent, and using the chain rule, I multiply by dx dt. And I know what dx dt is, it's 7. And then we need x, but it says when the area of the square is 64. So if the area, if that moment in time, so see this square is increasing. The moment in time when the area is 64, that means the side would be the square root of 64, which would be 8. So I'm going to substitute that in for x. And then I can solve. I've got the dx dt and I've got the x, so I can solve for dA dt. And it's 112 centimeters squared per second. Okay, now, this is a pretty straightforward one too. We've got a cylindrical tank with radius 3 meters. It's being filled with water at a rate of 4 meters cubed per minute. So we want to know how fast is the height of the water increasing. So I just drew a little picture of a tank and the water is increasing. We've got water coming in, and so the height of the water is increasing, and the water coming in is coming in at this rate. And we know that this tank has a radius of 3. Now, the tank is not changing in size, but what's happening is the volume of water inside the tank is changing. So the R is not changing in this case. Now in the balloon that was being blown up, it was changing, but the shape of this tank is not changing. So R is constant. So we need a formula that relates the height of the water to the volume and to the radius. So I think we have that somewhere. It's down here. This is the formula. So the volume of a cylinder or a tank is volume is pi r squared times h. So that's the formula we're going to need to use. I had just gone ahead and written out some of the things that we have. The volume is changing. So it tells me how fast the volume is changing because it's being filled with water at a rate of 4 meters cubed per minute. So that means that's the rate of change of the volume. And so that's my dV dt. So down here, and the dH dt, that's the rate of change of the height of the water. That's what we're looking for. Now we have our formula. And in this case, since the radius is constant, we can just go ahead and put it in and treat it as a constant and not treat it as a variable because it's not changing in this problem. with respect to time. So I just put 3 in there for the radius, and it's going to get squared because of the formula. So then I have volume equals 9 pi h. This is the formula that relates to quantities. So I'm going to do the derivative of each side. So over here, I have 9 pi times dh dt. And I know that the dv/dt is 4. So it's 4 equals 9 pi times dh dt. dh dt is what we're looking for. And so then I divide by 9 pi, and it gives me my rate, 4 over 9 pi. Okay, let's look at this problem. Sorry. Back to you. Okay, so here is a problem. It says a light is on the top of a 12-foot or 12-foot tall pole. So here's the light. And a 5-foot 6-inch tall person is walking away from the pole at a rate of 2 feet per second. At what rate is the top of the shadow moving away from the pole when the person is 25 feet from the pole? So you're going to need to draw a picture. So here's the pole and here's the person. 5 foot 6 inches is just 5.5 feet. So this is the person standing here. And so the light is going to make a shadow in front of the person. Now, the person is 25, that says 25, is 25 feet from the pole. And what we want to know, and we also know the rate the person's moving, we want to know how fast the shadow's moving. So we've got 2 distances. One is the distance that the person has gone, and one is the distance that the shadow has gone at this point in time. And so XP is the distance of the person from the pole, and XS for shadow is the distance of the shadow from the pole. And this leg of the triangle going all the way out to the tip of the shadow, we can call it X, but it's XP plus XS. Now we know that XP, he's 25 feet from the, he or she is 25 feet from the pole. So we know that XP is 25. So we also know that this is his distance, and the rate of change, the speed that he's walking, so that means the rate of change of the distance with respect to time is 2 feet per second. That was given right up here. That's the person's rate. And we want to know what is the rate of change of the shadow moving. So we want the dx dt, because if you think about, this is the distance from the tip of the shadow to the person. But this whole leg is the distance from the tip of the shadow to the pole. So we want to know how fast this is changing. So we want dx dt, the rate of change of the distance of the tip of the shadow from the pole. So let's look at this. And in this case, we're going to use similar triangles and not the Pythagorean theorem. So we've got similar triangles here. We've got the big triangle is 12, and on this leg, and then this leg is XP plus XS. And then the smaller similar triangle is this little triangle in here, and its height is 5.5 feet. And then this leg right here is just XS. Okay, so we can set up a ratio. So we can go 5.5 over 12, because those are like corresponding sides, equals the XS over XP plus XS. And then we can cross multiply. And so I'm going to cross multiply. So 5.5 times XP plus XS equals 12 times XS. I distribute and I collect like terms. So I get 5.5 XP equals 6.5 XS. And I just divided by the 6.5. So I have the XS, which I don't know what it is in terms of XP, and I do know what XP is. I know the distance of the person. So I just reduce that to 11 over 13. It's the same thing. And then X is the distance of the shadow is XP plus XS. So X is XP plus 11/13 XP, because that's what XS is. So really what we did here was we eliminated the variable XS. And so now it's just in terms of X, and X is in terms of XP. So X is equal, if I add 13 over 13 XP to 11 over 13 XP, I get 24 over 13 XP. So now this is the equation that relates the quantities. It relates this that I know this distance to this distance. And then we're going to have a rate of change. We know the rate of change of this distance right here. That's the rate the person's walking. We're looking for the rate of change of this distance right here from the pole to the tip of the shadow. So we're ready to differentiate. And I'm sorry, somebody's car is blowing. I differentiate right here. So I get 24 over 13 times d of xp, the person's distance, dt, and this is dx dt. Now, this is what we want. We want dx dt, and we're given dxp dt, because dxp dt is just the rate the person is walking at, and that was given at the beginning of the problem. It was 2 feet per second. So we know that dxp dt is 2 feet per second. So we substitute that in, and we substitute in the 2, and then we get 3.69 feet per second. That is how fast the tip of the shadow is moving at that instant in time when the man is 25 feet from the pole. Now here is one more interesting problem. And let me see, I'm gonna make it a little bit bigger here. Maybe. Let's read the problem. 2 people on bikes are separated by 350 meters. And this problem was already drawn out for us. So when they start, like person A starts here and person B starts here, there's 350 miles between them, or 350 meters between them. Person A starts riding north, so they're going this way at a rate of 5 meters per second. And then 7 minutes later, so they're not starting at the same time, but 7 minutes later, person B starts riding south. So person B is going this way at 3 meters per second. At what rate is the distance separating the 2 people changing 25 minutes after person A started riding? Okay, so let's call X, let's let X be person A's distance traveled by that point in time. So really that's 25 minutes after they start. And let's let Y be the distance traveled for person B after they start. And they start, oh, wait a minute, 7 minutes later, yeah, than person A. So then this is Y, and then this is X, because A is moving this way, B is moving this way. So that means this side, this is the X that person A moved, but this down here is the Y, because it's across, it's parallel to this line right here. So this is X plus Y. We know that this was 350 up here, so it's also 350 down here. And then we're looking for, what are we looking for? At what rate is the distance separating the 2 people changing 25 minutes after person A starts? So if person A is here and person B is here at the point in time that we're talking about. Z is the distance in between them. So we're really looking for the dz dt. Okay, so, and we do know person A's rate, and we do know person B's rate. So I'm going to call this one dx dt, because x is the distance that person A travels, and that's 5 meters per second. That was given. And then I'm going to call this one dy dt, because person B is going at a rate of 3 meters per second. So now I am going to use Pythagorean theorem. So this side is 350. If I look at the big triangle, this side is x plus y, and this side is z. Now, using the Pythagorean theorem, then z squared equals x plus y squared plus 350 squared. Don't square that out, just leave it like that. This is the equation. We're going to differentiate each side with respect to time. So I do that, and so I'm going to bring down the 2 times the z times the dz dt. And then I'm going to bring down the 2 times the x plus y times the derivative of the inside. The derivative of the inside is going to be the dx dt for the derivative of x, and dy dt for the derivative of y. And then the derivative of 350 squared is just 0. Now I can find x, y, and z, but what we want is dz dt. But I can figure out, first I need to figure out what x, y, and z are. Well, I can find x and y because I know the amount of time that they've been moving, riding their bikes, and I know their rate. So like x's rate was 5 meters per second, and that person had been riding for 25 minutes. So that's going to give me, and then I'm multiplying times 60 seconds in a minute. Why am I doing that? Because this rate is in meters per second, and this is in minutes. So I need to convert from minutes into seconds. So there's 60 seconds in a minute. So I get 7,500 meters. And then likewise, I know this rate, and I know that they have been riding their bike for 7 minutes less than person A. So 25 minus 7 is 18. And then I convert here as well. And that gives me 3,240 meters. So now if I think about it, so this side is x plus y. So I know what it is. I know that this is 350. So I can use the Pythagorean theorem to find z. So that's what I'm going to do next. So z is going to be equal to this side squared plus this side squared, and take the square root of that. That's using the Pythagorean theorem. I went ahead in this case and approximated that. I don't know, it probably doesn't make a whole lot of difference. And then I go back to my problem. Now I want to solve, because I want to go back to this one with the rates in it, because I'm looking for a rate. I can substitute z in, which I got right here. I can substitute in x plus y, and I can substitute in dx dt, which was given, and dy dt. And then that leaves the dz dt, which is what I'm looking for. And it's approximately 7.996 meters per second. Okay, I hope that you can do this now. And I will see you later.